Okay, let's start today's webinar. Thank you very much for joining the webinars. My name is Tulia from iNEMI. Today, we're honored to welcome speakers from India, Dr. Ji Jan. He will discuss the cooling technologies, the futures, team strategies for high-density AI and HPC platforms. Let me briefly introduce today's presenters. Details, please refer to this note. Dr. Ji Jan is a professional of advanced team technologies. He developed several alloys which are well accepted by the market. He published also the many articles and play a very important role in several professional associations. Abstract, Dr. Ji Jan discussed how advanced teams enable reliable heat management in AI and high-performance computing systems operatings at extreme power densities. So you will join the discussions of how metal-based and hybrid teams improve cooling efficiencies, mechanical stabilities, and long-term performance in demanding environment. About iNEMI's package webinars, we usually organize the webinars every month, but we not decided in December. Once the schedules will be fixed, we will inform you by email. About the iNEMIs, please visit the website or social medias, or you can contact with those peoples. You hold on. I need to accept. Okay. So at the end of the presentations, we will have a Q&A session. So please use the chat box and write your questions there. And for the presentation document, we will email to you with download link later. So please mute your lines during the presentations. Okay, Ji, would you start? Ji, can you? Ajay, I can't hear you. Would you? Okay, it looks you now. I'm mute, so please.
Yes, sorry about that.
Okay.
Yes. Thanks, Shreya-san, for the introduction, and thank you for iNEMI to provide me this opportunity to share my understanding of the team thermal interface material strategy for the high power density AI and HPC applications. So before I start, let me introduce our company. So Indian Corporation is a premier manufacturer and supplier of advanced materials. We believe that material science changes the world. At Indium, we develop and manufacture from solder materials to all kind of thermal interface materials, including indium preforms. We also have alloy and compounds. We work close with the customer to provide the solutions to help them increase yield and also reduce defects. Indium Corporation has a very broad product portfolio. We cover the semiconductor assembly, electronic assembly. We provide engineered solder materials, including preforms and heat springs. And we have a lot of different solutions for thermal interface materials for the thermal management. We also have metal compounds and high temperature solder materials. So today I will focus on the thermal interface materials. So at Indium, we have a world-class thermal team, including R&D scientists, application engineers, manufacturing engineers, and a very strong sales team. We develop industry-leading thermal materials and solutions to help the thermal management. We have a lot the equipment to do the thermal analysis in-house. We also have the facilities to run the reliability tests, including thermal cycling, power cycling, and host testing. Also, we work closely with partners such as equipment supplier and the customer to optimize the process. So here is the outline of my topic today. I will start with introduce the thermal interface materials and the types and how we select the team materials. And then especially for the AI and the HPC applications, so the GPU die, the size and the warpage changing for the thermal management. And based on that, I'll talk about why we need the mechanical team for this kind of applications, followed by different type of metallic team materials available in the market. And at the end, I have talked about the hybrid team stacking strategy and the liquid cooling options. So first is, what is the thermal interface material and why is that important? The thermal interface material is used between the interface between heat source and heat sink. Because this surface is not always perfect flat, that leaves a lot of air gap at the interface. So the air has very no thermal conductivity. In that case, we use team material to fill the air gaps. So in that case, we can improve the heat pass and help the heat transfer from heat source to the heat sink. Based on that, so here it shows the heat flow from the heat source to the heat sink. In this figure is from bottom to top. So between that, you have team materials and two interfaces. The total thermal resistance, including the thermal resistance at two interface, plus the thermal resistance from the team material itself. The individual thermal resistance is depending on how good is the contact at the interface, such as how many air gaps left there, and how the outside at the interface, and how the intermetallic phase can affect the thermal conductivity. And another part is the bulk thermal resistance from the thin material itself is depending on how thick the material we applied and the thermal conductivity of the material itself. And this showing the typical team architecture for the AI and HPC applications. So on the image for the image on the left, that shows the assembly. So there's one team materials applied between the die and the top lid. On top of the lid, so there's another team material we use to connect with the heatsink. So the team material used between die and the lid, we call the team 1. Between the lid and the cold plate, we call team 2. So that's the two different type applications you heard or not. On the right, so there is this configuration is you put the team material directly on the chip and connect with the cold plate. So there's no need between. So this situation we call the team 1.5, but you will also hear that somewhere called the team 0. So that it's the same configuration but different code. So for the team materials, so there are thousands of thermal interface material you can see in the market. And in this chart, I summarize the different type of the team materials. The top two rows as polymetric team materials, including the thermal grease, thermal gel, and phase change materials. So all of these materials are based on the polymer. So they are easy to use, but the thermal conductivity is very low compared to metallic tin. This kind of materials is widely used for Team 2 applications, so where the heat challenging is not that high. In the middle two rows, I list the metal foil and preforms. So that's usually the indium and the indium-based alloys. It has relatively very high conductivity. It's very special applications for the GPU, CPU, and also the liquid metal. Liquid metal is a gallium-based alloys, so it can used as Team 1 or Team 1.5. And also,
excuse me.
Yes.
Would you see the bottom of your screens? You can
Yes.
still stop sharing the one. The next, you can find the hide button. Would you? Yes. Yeah.
Okay.
Yes. Thank you.
Thank you. And there are some another kind of material based on carbon. So the graphite sheets and carbon nanotubes. So these kind of materials, they have anisotropic thermal conductivity at different directions. For example, the graphite, so it has very high conductivity in plane, but through plane conductivity is relatively low. For this kind of materials, the challenge is how you align the material in the z directions to increase the conductivity. And the last is the hybrid team stacking. So actually any combination of different type of materials together to achieve a certain application targets. I will talk that later. So these many type of team materials we can put together in this chart. Here, and this in 5 different categories in the chart. So the y-axis is the thermal performance. The x-axis is the we call the practicality. So it's including the cost and reliability, scalability, something like that. From this chart, you can see the metallic team, which are showing in the green triangle, green rectangles. So it has better performance and a better reliability and scalability. This thermal grease, thermal gel, this kind of polymer-based team, the cost is low and the scalability is high, but the thermal conductivity and thermal performance is relatively low compared to the metals. And the developmental materials such as diamond, graphite, metal hybrid, it has very high thermal conductivity, but right now is the manufacturing and the process is the cost is very expensive. So I believe in the future once once it's scaled up, probably it can shift to the right. So with high scalability and high performance. Because we have some of team material available, so how we select the team materials for specific applications. I list several criteria here. So first, you have to consider the conductivity. So that's totally based on how much heat you have and how much power you are using. What's the target thermal resistance? Based on that, the compliance, stability, and real workability you have to consider. But this adding together so give you the cost and the target of your applications. For example, here, so the best performance right now is the metal team, including liquid metal. So it gives you very low thermal resistance. But sometimes the process may be different from the polymer-based team. It needs a reflow or either dispense. And also another criteria is the surface compliance. So how the flexibility of the team can conform to the warpage of the die. And another is the reliability and also the bond line thickness requirement. So these are the criteria you have to consider when you select which kind of team material you are using. For the AI and HPC applications, so everything is based on the GPU. So here, this is GPU roadmap for right now. You can see the GPU is getting bigger. Not only getting bigger, but also there are multiple GPU dies putting together. For example, the Rubin, which will be released next year, has 2 GPUs, but very close to one radical. That's the so by putting that by layout the GPU together, you have at least a 50 by 50 millimeter area size. So that puts a lot of challenging for the warpage. And in the next step, probably the 4 dies and even 8 dies in the near future. So this not increase the area, but also increase the power to the whole system. On the right, you can see an example of the how big the warpage can be for this kind of big assembly. So the example showing here is a 4.8 radical SoC die. So putting together, so the total warpage can be 160 to 190 microns. So that's put a lot of challenging for the team materials. So why we need to consider warpage? So first, because of warpage, so the gap is formed during the warpage, and also for the warpage, you introduce a lot of thermal stress there. So for the team materials, it's need to have the compliance to accommodate the warpage in both directions. So you have to keep the contact of at 2 interfaces. And also the team materials will under the thermal stress that will put the challenging on the reliability. So because the warpage makes that the team applications very challenging. Here gives an example of the testing on the thermal test vehicles. It's a graphite sheet test on TTV, which has a die warpage of 125 microns. You can see at the 4 colors, the temperature is much higher than in the center. That's because as the colors, the warpage causes the gap between the die and the heatsink, and the team materials lost the contacts at the surface, which increase the temperatures very much. So based on the warpage we discussed previous, and here I give you the reason why we need the metal-based teams. So as we mentioned, the heat flow and the basic physics, the thermal resistance is coming from the interface also the bulk team materials. Here I show a chart the calculation based on the bond length thickness with the thermal impedance. Here I give 4 examples. The thermal grace, which showing blue, I put the number of 8 for the thermal conductivity. So that is nearly the highest thermal conductivity number the thermal grace can reach. And the liquid metal about 30, and indium about 86. Because the warpage from the CPU is in the range of 150 and 200 microns. So that means the thermal interface material is better to have a bond length thickness larger than that. In that case, you have enough material to accommodate the gap. For example, if we want to achieve 0.02 thermal impedance for the thermal grades with 8 watts meter Kelvin conductivity, you cannot go beyond 120 micron in bond length thickness. But for liquid metal and indium, you can easily go beyond 400 microns. So that gives you a lot of space to complement the warpage. So based on this chart, that means because of the higher thermal conductivity of the metallic tin, it can offer you larger bond length thickness to accommodate the big die warpage. So for the metal tin, it's here I list categories, 5 categories. So on the left is a solid tin, usually based on pure indium and indium silver alloys. So this kind of metal tin, you have to undergo the reflow process. The indium preform can be flux coated or without flux. The second category is the compressible indium preforms. So we call heat spring. So in this case, you don't need the reflow process. So the indium preform is put between the heatsink and the heat source with pre-node pressure. The third category is the liquid metals, gallium-based liquid metals. It has because it's liquid and easy to fill the air gaps at the interface. The next category is hybrid liquid. So we include that liquid metal paste on other liquid metal, either as filler or matrix. We'll call that as a hybrid liquid. So the last category is phase change metal materials. So this kind of metal materials has relatively low melting points. The melting range is between 60 degrees Celsius to 100 degrees Celsius. So depending on the compositions, we can adjust that. The advantage for this kind of phase change metal materials is it's solid at the room temperature and can get partial into liquid at the operating temperature. And solid at room temperature is easier for pick and place. And partial liquid at operation temperature can improve contact between the surfaces. So we talk about the metal tin. So the reason is why we use indium as the majority of the metal tin. That's because first it has high thermal conductivity, around 86 watt per meter Kelvin. And another advantage from indium is it's soft and very ductile. So that gives its advantage to accommodate the stress between the die and his sink. And another advantage is it has relatively no melting temperature, so that means you can reflow at relatively low temperatures. And based on that, it has good reliability for the assemblies. So the last one is the sustainability, because it's totally recyclable and reclaimable. So here to show you very basic sorting process. We have two different situations. So one is the pure indium without flux. So in that case, you have to apply the flux on both surfaces and then doing the reflow. For the flux coated preforms, you can just pick and place the preform onto the substrate and then do the reflow. So you don't need to spray the flux on both sides. And here I showed the since you have to consider when selects the sort teams. So first is the alloy, so indium or indium silver. So that's depends on the specific applications. And also the next is the flux, either bare metal or flux coated preform. Then the type is a solid or inform. So the inform it can help the bond length thickness to be uniform. And then the last variable is the thickness. How thick is good for your applications. So that's the things you have to consider. It looks complicated, but we have a very strong thermal team. Experts can help help you to select and optimize the process. So another category is the compressible metal team. So actually, it's indium foil with patterns on one side. The patterns we can change the shape and also the height of the profile. The advantage of this kind of materials is you don't need to reflow that. So just clamp it between chip and heatsink with pressure. And the pattern can help to fill the gap at the interface. So the resistance is usually decreased with the metal plastically formed at the interface. Now here I list the attributes for the heat springs. So it's made from indium, so has very high thermal conductivity. And there's no pump out issues and easy to handle. And we can provide in different thickness, so their conformability is pretty good. And you don't need to reflow, so the process is easy to handle. So the major applications for the heat spring is Team 1.5, the bare die to heatsink. And the most advantage part is the heat spring can be used for emerging cooling. because there's nearly no reaction between indium to the most of the emerging cooling liquid. We did a test of the compatibility of different type of teams with the emerging fluid. In the picture on the bottom, you can see after a couple of months, the indium metal is the only tin that doesn't react with the fluid. For the three thermal grease and polymer based tin, it's react with the fluid and getting dirty in for the emerging cooling. So that's really advantage from the heat spring. The next is the liquid metal as team. Because liquid metal is liquid at room temperatures, it's easy to provide better contact at the interface. The liquid can fill any gap. And also it itself has good conductivity. In the chart in the middle, so you can see the difference. The liquid metal helps the contact thermal resistance at the surface. The red line is just a pure indium pad put between the chip and the heatsink. But with the assistance of the liquid metal, you can see there is a dramatic reduce in thermal resistance. That's because the liquid to help the interfacial thermal resistance. However, the liquid metal has some challenges. It's the oxidation and also the leaking out. These are the things we need to address. The application for the liquid metal, so in the real applications, most commonly used is Sony PlayStation 5, as well as some high-end laptops with graphic cards. But this year, this January, so NVIDIA announced that they use liquid metal as team for their high-end GeForce RTX 5090 graphic cards. As you in the left bottom, you can see the disassembled 59 graphic card. The liquid metal used as thermal interface materials. As the edge of the chip, there they use a rubber barrier to keep the liquid metal in place. Then I'll talk about the hybrid team stacking approaches. Because the warpage challenging, so sometimes only one material cannot meet the thermal performance and the mechanical compliance and also the reliability. So in that case, we have to think about how to combine two or more teams together to achieve that goal. Example is the stacking is put indium, foil, and the graphite sheet together. So in that case, you have the both advantage from two different materials. So combine the rigidity and the flowability to maintain contact across the whole surface. And Also, that can help to address the boundline thickness range, reduce the risk of pump out. The majority of the hybrid team stacking is maintain the team 1.5 assembly over large bowl die. So this is the new area, and a lot of work is working on this area. So here shows the very common hybrid structures and its benefit. So for example, the Indian foils integrate with graphite or thermal grace, or sometimes even liquid metal. And also the graphite and the carbon nanotube can integrate with thermal grace, and liquid metal can use as a matrix or ether thinner to the nanowires, nanotubes, and also graphites. So both are to adding the different type of team together to achieve the balance of thermal performance and mechanical compliance. The practical deployment is about the team 1.5 application, so they need this high voltage dies. So we talk about all the team materials and types, how to select that, and then I will talk about how we evaluate the team materials. So for the team materials, the two most important things are effective conductivity and the thermal resistance. So this kind of testing is all based on ASTM D5470 standard. And the typical equipment available is here shows the example, the nano test TIMA 5. So in this machine, you can easily change the pressure, temperature, and the boundline thickness. So you can get the thermal conductivity and thermal resistance from different conditions. So another good tool for the thermal evaluation is the thermal test vehicle. So here I show you an example of this is our in-house designed TTV. So actually it's a silicon die which can be heated from 0 to 1,000 watts. In the silicon chip, there are a number of RTD detectors to monitor the temperature in the chip at different locations. And then we have the water cooling cold plate. So the system can run from 0 to 1,000 watts, and we can get the temperature profile from the die to see how effective is the team. Here shows a typical measurement from the TTV. This is running for the liquid metal at nearly 1,000 watts, from up to 6,000 cycles. The temperature is read from the different RTDs in the silicon chip and plot at the different locations. So in this case, that's showing the liquid metal has very good compliance to handle the big warpage. So for this TTV, the warpage is about 125 microns. Here I list the industry standards for different team materials evaluation and reliability. For example, the thermal shock, thermal cycling, Hess test, power cycling, and the vibrations. So these are the standards in the industry we have to follow. Last, I would talk about the new technology about the liquid cooling options. So there are roughly 3 different type of liquid cooling. The first is direct to chip cold plate. So that's usually used for Team 1.5 applications. The fluid is running from the cold plate. In this case, you still need the team materials to help the contact at the interface between cold plate and the chip. Another one is direct to silicon liquid cooling. In this case, so either the macro channel etched inside the silicon chip or on the back of the silicon chip, the fluid is flowing directly to the silicon chip. So this can give you very high thermal measurement. So, but right now is the process is expensive, and a lot of reliability tests need to be tested for this type direct to silicon cooling. So another is emerging cooling, as I mentioned previously. So it puts the whole system in the liquid. So that requires the compatibility of the team with the cooling liquid. So for all of the liquid cooling, there are 2 choices for single phase or 2 phase. But for the direct to chip, you still need the team 1 or team 1.5 selection for the team. But for the direct to silicon liquid cooling, there's no need for team. Here show you 2 examples of direct to silicon liquid cooling. On the right is the assembly announced by Microsoft in September. The macro channels are etched in the silicon and allow the cooling liquid directly onto the chip. On the right is reported from TSMC. So they integrate the direct to silicon liquid cooling with macro pillar array etched on the back of the silicon. So you can see the 2 different the difference here. The Microsoft one is etched inside the silicon, and the TSMA is on the back of the silicon die. But in both cases, so there's no interface separate from the for the team. So this is a very complex manufacturing process, and right now it's very expensive and still in the research stage. Now let me summarize my talk today. I talk about the team materials and the type and how we select the team, and specifically for the AI and the HPC, the GPU die warpage problems, and what's challenging this put on the team selections, and why we need the metal team. and the test standard for team material evaluation and reliability. Yes, thank you very much for your attending. I can take any questions.
Gee, thank you very much. And you received several questions, not in the Q&A box, but the chat box. So, Gee, would you go to a chat box?
Chat box, okay.
Yeah. Yeah. Then probably the okay, from Gene Cam Metal T maintains good contact during thermocycling size limitations. Starting from these questions. G.
Okay. So the metal team can maintain very good contact during thermocycling. Because it's after reflow, you have a very solid bond at the both interface. And based on the real application, we can select how thick for your for your applications, and we usually to select the thickness big enough to accommodate the mechanical stress. And the size and limitations. So the Indian preform can be as large as we can make probably 4" by 4" in size, and the thickness up to 500 microns. So the next question is, what surface finish at die packaging is Indian allergy compatible? So right now, the most applications of the surface finish as the die set is titanium nickel gold. So on the cold plate, you will have the annex surface finish. So for this kind of surface finish, the Indian preformed are very good at this surface finish, and also for other surface finish at the cold plate, it can also work. Have
Okay.
any news? Yes.
And the one questions from the forest, the which chart are you talking about for interface resistance?
Can you repeat that?
Yeah.
I saw that. How
Yeah.
are you taking into account the interface resistance in this chart? So
Probably
uh,
middle of
if
the
if
presentations.
this question related to to, the relationship of the boundary thickness and thermal impedance, that chart, I treat that we have the similar interfacial resistance at the surface. The change is mainly from the bulk material based on
Oh,
the.
okay. He said that the bond line thickness versus thermal conductivity is chart.
Yeah. So in that chart, we consider the interfacial resistance similar, and that's the difference is mainly based on the bulk material.
Oh, okay. And also testing the modifications. That's tough questions.
have any need for reliability test modifications? I think for the thermal cycling and high temperature storage test, we still use the same standard for liquid metal.
So you don't think the no needs to modify the existing standard method, or do you need to develop new test method?
So from the thermal performance point of view, so we only monitor the thermal resistance change during the thermal cycling. As long as the standard is, they just give you the temperature range and also how long you keep in that temperature. I believe that's it's totally depending on the specific applications, how what's the test parameters so this kind of application need.
Yeah. Okay. Thank you. And you have 3 more questions.
Yeah, so the now is interfacial thermal resistance can overwhelm the team performance. Can you quantify this or give an example? So for this interfacial thermal resistance, the very common issue is the voiding in the assembly. So that's you can check with the accuracy easily because the voids is where the air gap is. So if you have more voids, so definitely the thermal resistance will be higher. Another question is, so where do you see Team 1 progress from metal indium to liquid metal? Or something else when AI getting bigger? So for the Team 1 applications, I think the team material selection is totally based on how much heat you have. And the challenging is right now it's majority the Team 1.5 assembly for the big GPU dies, which is putting together the chiplet. So once that, for that, the metal indium team and the nickel metal can both use for that applications. And if the size gets bigger, so as I mentioned, if a single team material cannot meet the balanced requirement, some of thermal performance and mechanical compliance, so that's sometimes you need to stacking 2 or more team together to achieve that.
Okay, and probably that is the last questions about the with a consumer product. Better liquid.
For high volume custom product, is the performance gain of nuclear was the manufacturing result. Right now, if you see the applications for liquid metal, either Sony PlayStation 5 or the NVIDIA 5090, you check the images from the internet. All of these liquid metal applications, they came with a rubber barrier. So rubber barrier can help keep the liquid metal in place to avoid the leakage, and also can help the oxidation resistance of the liquid metal.
Mm. Okay. Oh, okay. Probably it's time. So that was very good discussions. Thank you very much, everyone. And before we close this webinars, everyone, would you go to the React icons and give him the big hand?